Page 3 of the addendum for integration. First, we're going to demonstrate that this is true. This is pretty easy to go in this direction. Go the opposite direction a little bit harder. So if you are going to combine two fractions with different denominators, you would want to make them into a common denominator. So I'm going to multiply the first one times x minus 2 on top and x minus 2 on the bottom. I'm going to multiply the second one by x plus 2 on top and x plus 2 on the bottom. And then I would get 3x minus 6 for the first fraction. And I got, remember, x minus 2 times x plus 2 is a difference of squares. So you would get x squared minus 2 squared, which is 4. And then the second fraction would be x plus 2 in the numerator and x squared minus 4 in the denominator. And then we have now shown that, let's see, 3x minus x is 2x. Negative 6 minus 2 is negative 8. So we have shown that that is true. Okay, and now that we have shown that that's true, when they ask us to find the integral of this, and you can see that if the top was 2x only, that would be something we could take the integral of easily because that would be the remainder of the chain rule on top. It's not, so we need to use this identity that we just demonstrated. So instead of putting this, I'm going to put the equivalent expression, 3 over x plus 2 minus 1 over x minus 2 in the middle of the integral. And I'm going to take the integral of each one of these because you can see that if I take the integral of each one of these fractions, then there is no chain rule remainder necessary because let's say, if I consider it 1 over u, the integral being natural log of u, I can just do, okay, natural log of x plus 2 times 3 for that one, minus the natural log of x minus 2. And the derivative of that would be that one, right? And if you take the derivatives and check it, everything works out, right? The chain rules of x plus 2 and x minus 2 on the interior of these natural logs is 1. So, okay. That wasn't too bad, was it? Now we're going to be starting integration by substitution for some of these expressions that you are more complex than just a linear function. So we've done like these kind of functions in the core. We're going to be doing more complex functions now, okay? So let's look at this first one. And they're going to give you guidance here, which makes it a little bit easier. They tell us what the u substitution is going to be, okay? So let's rewrite this integral here using this substitution. So I'm going to substitute x minus 1 over x to be u. So instead of the integral of that awful looking function, I'm just going to have integral of e to the u divided by, and let's see, x squared. What would I substitute in for x squared? Well, let's see, u is equal to 1 minus 1 over x, basically, right? If I try to solve for x, I would get u minus 1 equals negative 1 over x. 1 over x equals, I'm going to multiply everything by negative 1. I get 1 minus u. And if I want to solve for x, I get x equals 1 over 1 minus u. So I do need an expression for x squared to do the substitution. Let me make some more space here. So x squared, which is what I need, is 1 over 1 minus u squared, right? So I'm going to put that in for x squared, and you notice x squared is in the denominator, so it would actually be 1 minus u squared on top. Last thing I need to substitute for is dx. Let's take this expression here, u equals 1 minus 1 over x, and let's take the derivative of both sides with respect to x. So the left side would be du dx, and the right side would be the derivative of 1 with respect to x would be 0. Negative 1 over x is negative x to the negative 1. So we would, let's see, we would get that for the derivative of negative 1 over x with respect to x. And then, so that would be du equals dx over x squared. And then we could say that dx equals x squared du. And then if we wanted to put the x squared in terms of u, we could substitute in this expression that we already have here. So we would have dx equals x squared, which is 1 over 1 minus u squared. Yeah. So, by the way, I wrote this wrong here. Did you see? This should be 1 minus u squared, right? Yes. And then this should be 1 over 1 minus u squared. Okay. And so now I'm going to substitute in for dx this expression here, du divided by 1 minus u squared. So, oh, that's interesting. Look at that. I'm going to substitute in for dx. I'm going to put this, and then these cancel out, right? That's not very good too. Okay, and this cancels out with this. So we're left with the integral of e to the u du, which is just e to the u. And now we're just going to substitute back in the x in for the u, so it would be this expression here. So it would be e to the 1 minus 1 over x is the answer. Okay. I'm just going to shrink these down because I need a little space below. Okay. Let's look at this one here. So find the integral of this expression here. Now, I can see something going on with the bottom and the top being related, right? If I take the derivative of the bottom, I would get negative 2x plus 5. And you see how negative 2x plus 5 is kind of a multiple of that one? So it looks like our u substitution could be the denominator here. So I'm going to do a u substitution of 5x minus x squared. Du would be 5, or du dx is equal to 5 minus 2x, right? And then I could multiply both sides by dx, so then I would get du equals this times dx. So I could do, let's see, dx is equal to du divided by 5 minus 2x, right? So I could substitute this in for the dx, and let's see what I get. So I get 4x minus 10 on top. And on the bottom, I have u because I can substitute this with u, and then my dx becomes du divided by 5 minus 2x. And let's see, the 5 minus 2x, remember, is kind of related to 4x minus 10. If I factor out a negative 2 from the 4x minus 10, I would get negative 2x plus 5 on top. And on the bottom, I would u, and I would also have negative 2x plus 5 on the bottom, right? And so these would cancel out. And then I would end up with the integral of negative 2 over u du, which is just going to be equal to negative 2 natural log of u plus c. Oh, by the way, up here, the answer would include plus c, right? Because it was an indefinite integral. And now I substitute back in for the u. 5x minus x squared. So my answer is going to be negative 2 natural log of 5x minus x squared plus c. So this is my answer. Just going to shrink this down, make a little space. Okay? All right. Let's do this one. 1 minus x squared on top, x cubed minus 3x on the bottom. Again, do you see how if you take the derivative of the bottom, you get 3x squared minus 3? 3x squared minus 3, wow, that looks a lot like the top one. If you factor out a 3, x squared minus 1 on the bottom, 1 minus x squared on top, they're just multiples of negative 1 of each other. That looks really promising. So let's do a u substitution where u is equal to the bottom. And then we know that we're going to be able to use the derivative of that to do a substitution, which is going to help us. Let's set dx equal to du divided by 3x squared minus 1. And then we'll do the substitution for this dx here. The bottom, we're going to substitute with u. Top is going to be 1 minus x squared. The bottom is going to be u. Dx is substitute for du divided by 3x squared minus, 3x squared minus 3, right? That's 3. Then we can factor out a negative 3 from this expression here, and we'll get 1 minus x squared on top divided by u, and negative 3 and 1 minus x squared on the bottom, du. And then we know that this and this cancel out, and we're left with something quite simple, integral of 1 over negative 3u du. Okay, and let's just shrink that down. Okay. We're very close now. The integral of du over negative 3 du is equal to negative 1/3 natural log of u plus c. And then we substitute back into u, the u substitution x cubed minus 3x, so we have negative 1/3 natural log of x cubed minus 3x plus c. Okay? All right. Let's square around it. Okay. That wasn't too bad. Next one, integrate with respect to x. So we have x e to the 1 minus x squared. Look at that. If we take the derivative of that, we're going to get like negative 2x, which kind of looks like what we have as the remainder of the chain rule here. That looks perfect. So what we're going to do is we're going to replace this part with u. If that part is u, du dx is equal to 0 minus 2x, right? And then so dx is equal to du divided by negative 2x. Then we're going to substitute, and then we're going to take the integral, okay? So if we take the integral of this, we're going to replace this dx with this dx expression. So we're going to have x, and then e to the u, because we replaced 1 minus x squared with u. We replace dx with du negative 2x. And wow, we cancel out these x's, so we basically get integral of negative 1/2 e to the u du. And the integral of that is negative 1/2 e to the u. And so, plus c. And then we just need to put the u back in. So the u is 1 minus x squared. So negative 1/2 e to the 1 minus x squared plus c. Okay? Not too bad. All right. Let's do this one here. Integral of natural log of x cubed divided by x. So this looks kind of suspicious. 1 over x. 1 over x is the derivative of natural log. So it looks like the u could be natural log of x, and the du dx could be 1 over x. Right? So dx is equal to du times x. Right? Just cross multiplied there. So I'm going to replace dx with this expression here. I'm going to replace natural log of x with u. Okay, let's do that. So we'll have u cubed of x on the bottom. We're going to replace dx with x du. Hey, these cancel out. Cancel out. So we're left with the integral of u cubed is u to the 4th over 4. And then we substitute back into the u to the 4th, which is u equals natural log of x. So we have natural log of x to the 4th divided by 4 plus c. Okay? That's good. Let's do the integral of sine to the 5th. Now, when you have a power like this, what you would like to see is like maybe a cosine or something out here so that you would have the remainder of the chain rule of the power rule, and we don't have it. So you would like to see a mixture of cosines and sines, right? Let's do this. So like remember the identity sine squared plus cosine squared equals 1. So this actually gives us the flexibility to introduce the cosine. When we just have a bunch of sines, we can introduce cosine whenever we want to by using the identity sine squared equals 1 minus cosine squared. So we could like take some of these sines and replace them with cosines by doing that. So let's try that. So instead of sine to the 5th, we're going to change it to sine squared times sine squared times sine. Each one of these is x, okay, dx. And then we're going to replace sine squared here and sine squared here with 1 minus cosine squared. So we'll have the integral of 1 minus cosine squared x squared sine x. I still don't easily see how the chain rule of the inside of this is going to result in sine x. So let's expand this. So instead of 1 minus cosine squared x quantity squared, I'm going to put 1 squared minus 2 cosine squared x plus cosine to the 4th x. And that's going to be multiplied times sine x dx. Now I'm going to distribute the sine x. So now I'll have integral of sine x dx. I'm going to have negative 2 times the integral of cosine squared x sine x. And I'm going to have the integral of cosine to the 4th x sine x. Now I can start seeing like how some of these are going to work out. Like for example, the integral of sine x dx would just be negative cosine x, right? Let's check that. The derivative of cosine x is negative sine x, so negative cosine x, the derivative would be sine x. Yes, that worked. This one here, I could do a u substitution. U equals cosine x, so du would be cosine x dx. I'm sorry, negative sine x dx, right? Negative sine x dx. So, if I do the substitution, I would have minus 2 integral u squared. I'm going to substitute sine x with du divided by negative sine. So I would put du divided by negative sine x. And I originally had a sine x here, so the sine x's cancel. And then I'm left with negative, the negatives cancel too. So I would end up with positive u squared du with a 2 in the front, right? And then the next one, I'm going to use the same substitution here. I would get integral of u to the fourth, and then sine x, and then I would substitute in for dx. I would put du divided by negative sine x. So du divided by negative sine x. So the sine x's cancel, and then I'm left with negative integral u to the fourth du. So my integral of that would be negative u to the fifth divided by 5 plus c. And then my u squared du, my integral will be 2u cubed over 3. Okay. And the first one is negative cosine x. We already know that, right? And now we can just substitute back in our expressions for u. So, u, if you remember, is equal to cosine x. So our final answer would be negative cosine x plus 2 cosine cubed x divided by 3 minus cosine to the fifth x divided by 5 plus c. This last one doesn't look too bad. Remember, if you have a mixture of sines and cosine, that's kind of a good thing, right? So we could say, oh, this looks like has something to do with u, and the du looks like it might be this, because it looks like if you take the derivative of the inside of sine cubed, which is sine, you would get cosine, right? So let's try the substitution u equals sine of 2x. And then du would equal to cosine 2x times 2. Okay, that looks promising. Let's try that. So this inside part is going to become u cubed. The dx is going to be replaced with du divided by 2 cosine 2x. And look, it cancels out with the 2 cosine 2x on top. Oh, with just the cosine 2x, but the 2 stays. So basically what we get is, we get the integral of u cubed du divided by 2. So the integral of that would be u to the fourth divided by 8 plus c, and I'm going to put the expression in for u back again. So I'll have sine to the fourth 2x divided by 8 plus c. Okay, so that's it for this page.